Hey everyone, I'm happy to present a paper on many-joint robotic arm control with recurrent spiking neural networks here at IROS 2021. The paper is authored by Sebastian Otte, Robert Legenstein and me, Manuel Traub. Sebastian Otte and I are from the University of Tübingen from Germany, and Robert Legenstein is from the Graz University of Technology from Austria. And so I'd like to start off with a short teaser. Here on the right you can see a simulated 6-joint robot arm, and the movement of each joint in the simulated robot is controlled by 3 servo motors that each drive a linear gear. And each of those linear gears is connected over a ball slider mechanism with the base of the next joint. And by now adjusting the linear gears, a joint can approach any combination of tilt angles along the x and y axis in the range of -40 and +40 degrees. And additionally, a joint can alter the distance to the next joint, whereby the approached angles limit the movable distance and vice versa. The overall movement of this robot is also controlled by a spiking neural network, from which you can see the moving spike train here right beside the animation. And unlike your typical artificial neural networks, spiking neural networks are more like a continuous simulation of more biologically plausible neurons over time. And these neurons communicate over distinct events in time called spikes, which you can see here on the plot on the right. And while these spikes here move over the screen, the network continuously predicts the position of each joint in the robot arm starting at the base. And these predictions can be used in order to adjust the pose of the robot using backpropagation through time and gradient descent, which lets us steer the robot. But let's start at the beginning with the architecture. We use a so-called long short-term spiking neural network proposed by Belek et al., which is a kind of recurrent neural network, and it is composed of adaptive and non-adaptive leaky integrated fire neurons. And the training of this LSNN, to which I come in a minute, can be done with a few tricks in your regular autograd framework like PyTorch, for example. And since we directly input real values as a weighted input current into the network, and the fact that it already produces real value outputs makes the LSNN a really good drop-in replacement for your standard recurrent neural network like LSTMs, for example. And in fact, Belek et al. Showed that for many toy problems, an LSNN approaches and in some cases even surpasses the performance of classical LSTMs. And so as I mentioned, the first kind of neuron in an LSNN is a so-called leaky integrated fire neuron. And these neurons are a simple and computationally cheap type of spiking neurons which work here according to equation 1 and 2. And here the voltage of a neuron Vj over T is computed as the leaky integration of the weighted inputs Ij. And after a spike, the neuron J is resetted by subtracting the value of the spike threshold. And this behavior can also be seen here in the bottom, where a neuron is simulated with a constant input current, and therefore its voltage increases until it reaches the spike threshold, where it then emits a spike and the voltage gets reset and the whole process starts again. And the leaky integrated fire neuron is also very similar to the real value output neuron of the LSNN, which is called a readout neuron. And this is basically a leaky integrator without the reset term here in equation 1. And I now want to briefly introduce the second kind of spiking neurons, the adaptive leaky integrated fire neurons. And these neurons now add a little bit of additional complexity in order to simulate the spike frequency adapting behavior of real biological neurons. And so observation in the mammalian brain found that some type of neurons get less and less sensitive for incoming spikes if they themselves fire more rapidly. And here in the bottom graph you can see that the adaptive leaky integrated fire neurons simulate this behavior where the time between successive spikes increases when the neuron receives a constant input current. And this behavior is generated by increasing the base threshold for each individual neuron, here based on equation 3 and 4. And here we first compute a low-pass filter of the neuron's own spike train, and then we add the value of this filtered spike train multiplied with the constant beta to the base threshold. this then increases the neuron's threshold after each on spike. And with no further activity, the neuron's threshold then decays back to the base threshold. And the key takeaway is that through these equations, an LSNN is able to preserve and backpropagate gradients over long distances back in time. And particularly the decay constant of the threshold controls how long we can backpropagate gradients before they also decay over time. And so you might now be wondering, how can we even train these spiking neurons with backpropagation through time? Since the individual spikes are computed with a threshold function, and this threshold function itself is non-differentiable. And here, Bellick et al. Uses a clever trick by employing a pseudo-derivative in place for this non-existing derivative of the spiking function. And this pseudo-derivative, which is also plotted here in the bottom graph, is a simple triangular function of the voltage, and it has its maximum when the voltage exactly matches the spike threshold. In order to now control the movement of the simulated robot, we first train a forward model which learns to sequentially predict the position and orientation of each joint in the robot given the motor states of that specific joint. So starting at base, the LSNN gets the motor states inputted over a certain time window, and then during the last time step of this time window it receives an additional one hot vector indexing this current joint. And during these last time steps, the network then outputs the position and orientation of that joint. And after this, the network then progresses to the next time window, where it then progresses the next joint. And this continues until we reach the end effector, where the network then, within the last time steps of this last time window, outputs a prediction for the position and orientation of this end effector. We now then train the forward model with backpropagation and randomly generated arm poses. And we also, to a certain extent, mix in some edge cases, like heavily twisted arms, for example. And once we have a trained system, we can then use it for motor inference. And here we now predict the position of the end effector based on the current gear states. And now, in contrast to the training procedure, where we would backpropagate the discrepancy between the predicted position and the actual position, instead we now compute the error between the predicted end effector position and a target end effector position. We then backpropagate this error back through the network and back through time into the inputs. And for these inputs we now get an input error with respect to this discrepancy between the predicted position and the target position. And we can now optimize these input errors with a gradient descent technique and thereby adjust the gear states of the robot, which then leads to a steering of the robot's end effector towards our desired target. And we can also do this for the orientation, where we again compare the predicted orientation with our target orientation and then backpropagate this error back to the network into the inputs. Also, since we know the actual position of the simulated robot's end effector, we can perform a so-called target correction step. And here we move the target just a little bit before we compute the output error in order to correct for the prediction error of the network. And this then leads to the robot missing the alter target just in such a way that it moves the end effector closer to the actual target. And while this is easy in the simulation, in the real world we would have to use something like a visual feedback system, which also returns the actual position of the end effector. And so now here on the right you can see this whole process in action, where the simulated robot continuously approaches different targets and the network optimizes this simulation. And in our paper we evaluated in detail the accuracy of this inference simulation in terms of position accuracy and orientation accuracy. And while position accuracy can get below 1 mm within the simulation, the orientation accuracy is not that accurate. And you can see this in the graph here, where the position accuracy is plotted in blue and the orientation accuracy is plotted in brown. And besides the short simulated arm, which has the same number of joints as the one we 3D printed, we also tested much longer simulated arms with up to 25 joints or 75 degrees of freedom. And even with these long robots, we achieve a mean position accuracy of just above 1 millimeter. And in our paper we also presented two 3D printed robots, where you can see the bigger one here, right beside me, in original scale. And both of these robots, except for the motors and the electronics, are completely 3D printed, and the total material cost for each is less than 500 euros. And the robots are controlled by several Arduino microcontrollers, one for each gear, which are all connected over an inter-integrated circuit. And in order to control the movement of these 3D printed robots, we just copy the gear states from the simulated robot over to the real robot, which then performs the same movement as the simulated one. And so with this, I'd like to thank you for your attention and end my talk with an additional demo.